In this video, I briefly talk about the big M constraints in integral programming, and also several slides to talk about the logic constraints in integral programming IP. We still use a facility location problem as an example to explain the big M method. So quickly review the facility location problem. Suppose we have M customers who needs to be served from a facility. Suppose we have n potential facility locations or sets, and then CIG be the cost of serving all the customer G's demand from facility I. Let Fi be the operating cost of facility I per period, so it's kind of fixed cost. Now we would like to set up an integral linear programming model to minimize the total cost of serving Syncover's customers and open facilities and operating these open facilities. So it's like the decision to actually decide how many and which facility to open. So previous facility location problem we introduced as below. So we defined the serial variables xi, binary variables. So the value is either 1 or 0, and the xi equals to 1 if facility I is open, otherwise equals to 0. So you have n potential locations. Yig, also binary variable, equals to 1 if customer J is assigned to facility I. So we have a model, minimize the total cost. So this is, for example, transportation cost. This is operating or fixed cost. And then we have a constraint Yig equals to less than Xig. So this is a typical logic constraint. We're going to explain more about logic constraint or relations or statement. So here basically Yig less than or equals to Xi, make sure if Xi equals to 1, that means facility I is open, then Yig can be 1 or 0. And if Xi equals to 0, then Yig must be 0. So that's actually the meaning of your constraint. And then we have second constraint, sigma Yig equals to 1. So you sum up all the customers and service decisions, then each customer only allowed to be served by one facility. Here is the example we used in the Excel screencast to explain how to solve the facility location problem. So here we have the transportation costs, all these numbers, and then we have fixed cost for your each facility. And so based on the previous model, now we can actually try to explain a big M constraints. So previously we have actually Yig equals to Xi. So if we take an example, Y11 should be less than X1, Y12 should be less than X12 1 should be less than X1, and then you actually have Y15 should also be less than X1. So if we sum up this constraint together, you actually can see we sum up YIG by your total customer numbers should be less than 5xi. And then, so here if we substitute this 5 by m, capital M, now you actually can reduce the number of your constants, the total constants. So this is just an intuitive explanation. It's not really theoretical explanation. You just try to understand how did we sum up the multiple constants. So here, the purpose actually is to explain. Now we can transform YIG less than xi into a new constant by using a big number m. So we assume m is a sufficiently big number. So now we can use a new constant. This constant normally is called a big M constant. So now we have an alternative facility location model. In the Excel spreadsheet, I have tried to explain how to solve such a problem. So in our example problem, so you have 5 customers, 3 facilities. Then you can think about this m can be something greater than or equals to 5. Apart from mathematical explanations, we can also explain the big M constants by the logical meanings. So initially we have our constant YIG less than equals to xi. This just ensures if a customer is assigned to a facility that the facility is actually open. Now if we use a big M constant, so now we consider facility I. If any customer is assigned to the facility I, then this must be YG equals to 1. If you actually have customer 145 assigned to facility 1, then you actually have multiple YIG equals to 1. So the left-hand side of the constraint, sigma YIG should actually less than the sum up of the MXI. Then make sure the number of customers assigned to facility I actually is less than make sure xi is open, then you can actually assign multiple customers to this facility. So then the constraints ensure facility I is open if you can if you want to assign customers to this facility. And also, we assume that no customers are assigned to the facility if xi equals to 0. So this constraint make sure both the original logical relations we required. So for the specific problem here, we can choose capital M equals to a constant number, and for all the feasible solutions to the problem. For example, m equals to 5 or 6 or 10. In other problems, it should be carefully chosen based on the problem parameters. We can also see another example. So now we modify the facility location problem. So we actually still have xi as a binary variables about whether you choose to open a facility in location I. YIG is actually no longer a binary variable for assigned customers to facilities. So here we actually talk about a fraction of demand in customer J to be assigned to facility I. So we allow you to actually assign the part of the customer from one customer to your facility. So we can see objective function are same. So we still use the constraint sigma YIG sum up by G less than or equals to MXI. So here we can see we have a new constraint about YIG. So the total YIG assigned to one facility I actually, to one customer equals to the demand of your customer. So here we actually should add one parameter. DG is the total demand of customer J. So this constraint makes sure all the customers' demand will be served, will be actually satisfied. And then here actually semantics, so YIG is no longer binary variables, XI is binary variables. YIG should be non-negative. So that's actually a modified facility location problem. In this example, your M can actually take the capacity of the facility. So when the capacity is not specified, then you actually can give a sufficiently large number. So if capacity is not specified, then you need a really large number. Otherwise, you can take capacity of the facility. So this example is similar with the settings in our case for Go programming. So if you don't get that now, it's okay. So we'll look into that later. When we talk about integer programming, this actually very often we need to deal with logic statement or relations in your problem. So here, for example, a logic statement denotes an expression which is either true or false. For example, facility I is not open, or customers are supplied by facility I. So operations I is finished, product I is produced or purchased. So these are the logic statements can be combined to form a logic relation. So these are the logic statements. So yes or no, your answer is 1 or 0 or yes or no. And the logic relations actually combines multiple logic statements. So for example, here we see if facility I is not open, then customers cannot be supplied by facility I. So you actually should have YIG less than XI. That's what we used in the facility location problem. Or we have sigma YIG less than MXI. So second operations I must finish before operations J. If we produce product I, then we must also produce product J. So if we buy product I, then we must buy at least N units. So that's some examples about logic relations. And the next slides we talk about how to model this logic statement or relations by binary variables. We use the example of a knapsack problem. So we suppose to have n projects, and you need to make a decision to decide to invest on which project. So each project J actually costs WG to invest. Investment G has an expected payoff of PG. So you have a payoff, you have a cost, you have a budget. Now we have a budget of C krona for the investments. Now set up an integer linear programming problem that maximizes the total expected payoff without violating the budget. So the original. Now we try to extend the knapsack problem by adding some logic constraints. So let's see. If we have S1 means project 1 is chosen, S2 means project 2 is chosen, R if project, so relations is R, if project 1 is chosen, then project 2 is also chosen. Then we define the decision variables xj. So then x1 equals to c, x1 equals to 1, s2 equals to c, x2 equals to 1. And then r means you actually, if s1 is true, then s2 is true. Or equivalently, we see x1 equals to 1, then x2 equals to 1. How can we actually combine these conditions? So how to write it? So here we actually have a list of the logical constraints for you to choose. For example, for the knapsack problem, we have either project 1 or 2 is chosen. So if x1 is chosen, then x2 is chosen. That's actually this statement. If x1 equals to 1, then x2 equals to 1. Then we actually should write x1 less than or equals to x2. You can actually verify this by if x1 equals to 1, then this constraint makes sure x2 also equals to 1. And if x1 equals to 0, then actually x2 can be 1 or 0. So this condition is an only result from this logic constraint. There are also multiple others. For example, either project 1 or 2 is chosen or both. Then you can do x1 plus x2 greater than 1. We also can try so for example, this at least k projects must be chosen. Then you actually can write sigma xg actually greater than or equals to k. So we did not have this constraint in the knapsack problem, but you can add this constraint. You can go through the rest when you need them. You can just pick them up.